Hello. I'm gonna just get set up here real quick. One day I will figure out how to get started without delay. We're gonna be going over Elixir Nerves. I spent a little time learning it on my own. So this time we should be able to review some of it just to show where I went wrong in the last stream. And hopefully that'll be good. All right. Huh. Why don't I see myself in Twitch though? Channel. Offline. Although it says it's streaming. I'll just have to assume it's working. All right, so I have this Raspberry Pi Zero, and I did lots of things wrong in the last stream. So we're going to kind of start over, and we'll see if we can get it working from kind of scratch. But just to show you that it's working right now, I have an SD card in here. When I started, I didn't even know like which way to put it in, right? Like here's the card. It's in now, and I'm going to plug it in. Let me take this power cord. And it has the firmware installed and a Blinky program. It's like the Hello World. That's going to make the green light on here actually blink. So that's what we'll do. Hey Findus, how are you? How are you doing today? And on the Raspberry Pi, you have the SD card. This is the Pi 20W, and that's important because I sent Nerves the wrong target hardware. So we'll have to remember that for later. So we have to know it's a Pi 02W. And then when you look at it, you have the card up here. The power goes on the furthest micro SD input. So I just plug that in. And when I do that, you should see like this light come on briefly. That means activity. It's reading from the thing. And then it boots up the firmware and starts executing the program. And then that was about, what, 20 seconds or something? And it starts blinking, right? So you see it's blinking now. We know that it works. So we're going to try to recreate that whole thing from scratch to make sure that we are able to do that. And then I actually learned something. It's good to review, right? Otherwise, you just follow the instructions and you have no idea if you actually learned anything. Okay. All right. I didn't really plan this so much, so let's see how we should be doing this. We'll go into a terminal screen here, and you can see the terminal. We have getting started from Nix here, Nix Nerves. Not Nix, what am I saying? Elixir. And I want to be able to see chat, so I'll leave this here. Maybe I'll leave it here. All right, I think I'm set up now. I'm assuming the audio is coming through okay. So we made a nerves directory, and we'll call this like redo. And we'll kind of just start from the nerves guide here, just to make sure that we understand what's going on. Nothing, getting started. This is the first part, right? Yeah. We'll skip this, creating a project. So I think what we want to do, yeah, let's follow these instructions. So mix, instead of new, which Elixir usually does, we do nerves new, and we say hello nerves. This creates a new nerves project for us. And then we say install the dependencies, so it does a mix steps get for us. All right, project successfully created. This kind of helps you out, but the instructions, what did it say? X command, failed to execute. Please run the following command again. We don't have a mix project because we didn't go inside. Anyway, we go inside, and then before we run mix steps get, we need to set this mix target, right? And that's where we look inside the thanks, Findus, supported targets page. And my big mistake was I saw pi 0 and pi 0w, and I was using this target, right? But the correct target is, if you scroll down a little bit, it's actually under pi 3a that you need to do. So we're going to be using RPI 3a. So we'll go ahead and set that mix target. RPI 3a. And then we do mix steps.get, and that will use the mix target to pull in what we actually need. Mix target RPI 3a, that worked out. Yeah, this is just saying you can pass in the environment variable directly. And now we can actually make the firmware. So here we're going to make the firmware. Since I already exported it, mix target, we don't need to send that in. We just do mix firmware. And then that should create the actual executable that's going to use. However, I want to do one thing before we do that, because I want to be actually connect to this, right? This image, or this operating system that it's running, this Elixir VM. And the way to do that is we need to edit the vintage Wi-Fi setting. That way it'll actually like connect to our Wi-Fi. Here it is, connecting to your nerves target. I think that's in here. Where was the... Funny. Because there should be something in here under config, and then we look at target.exs, and in here we have this config for the network, and we need to turn this on. I'm surprised it doesn't mention this here. Am I just not seeing it? Oh, here it is. It uses vintage net direct. Vintage neck, if net. All right, maybe that's something else. And in here, we just need to add the info for the Wi-Fi. And I made a GitHub just for this, I think. I called it, this is my next Nerve Shell one. Configuration. Oh, maybe I didn't create one. Let me find it somewhere else. Oh. I don't know where I put it. Let's try to figure out how to do this then. So we look for new Ethernet service. Nerves pack dependency simplifies it. So we just need to figure out how to use this thing. Services, MDNS, SSH port, optional Wi-Fi wizard shortage. Well, I'm gonna cheat. So I did it in here earlier. Under nerves examples. No, I did it under nerves install. And I made hello nerves. And I'm pretty sure I edited the config target.exs. Yeah, so here is the info, and you can see my Wi-Fi password in here. So be careful, don't get my Wi-Fi. Let me just copy all of this. And for next time, we'll add it into a gist in here. So we'll make a new one. Nerves Wi-Fi. And this is the part we need to put in here. And then we create the gist. Why did that not work? Today's not a good day. What's going on today? All right, that worked. So we just need to add this part to the other config, but I only need the WLAN 0 part. Which means I can just delete this and paste. Oh, it didn't copy it. Selected register. That's in there. And then I should be able to paste, right? No. Oh, I know. I'm just being silly. Okay. So now we have that in there. I think that should work. I think I just need to rebuild the firmware. Let's go back to the original Project Nerves redo. Hello Nerves. And now we do mix firmware. The other thing that I needed to do that didn't work was that in my packages that I have installed, there was a bunch of packages I needed to add to Nerves. Now, whether you're using Nix or some other OS, you know, you basically need makefile, fwup, gcc, gnumake, rebar3, squashfs tools. Yeah, and this one got me screwed up because KDE ask pass is when it needs sudo access. It defaults to X11, but I don't have X11 installed. I just have Wayland. So this package will bring up the Wayland version. And additionally, I think I made a shell.nix, which adds these two variables that, you know, are kind of useful for me, especially this one, the sudo askpass. You need that for it to actually use the askpass program. And you'll see it do that when we actually try to burn the firmware. Okay, so we have the firmware. It says it's successfully built. We all see that. And now we just need to actually put it in the SD card, right? Let's just make sure we're following the instructions. Now we do mix firmware burn. So I take the SD card out of the thing. I have a little SD card reader writer on my laptop. So I put that in there. On my desktop, it pops up something that says I've inserted removable media. So that's the sign for me that I know it works. And then I do mix firmware .burn. I think that's it. Let's go. And it found dev SDA, which is the correct device, and then it asks me for my password. It brings up something on my screen. Let me see, I can show that. No, my desktop doesn't work. Oh well. But it is asking me for my password. I gave it, and now it's using the memory card. It's all good. It burnt. Oh, there was one other thing I had to add into my Nix config. How come? Let me see here. It wasn't this. It was this. Avahi. I needed to add this, and I think this is so that it can use what we're just about to do now. Which is, I think, connecting through nerves.local. So I can do ping nerves.local. Oh no, I have to put the card in. It's so hard to take these little things out. And now I put the card in here. and then I plug it in. And hopefully you'll see this actually blink on and then off. So here it's on and then it goes off. So the off means there's no activity, which is a good sign. What was going on before was it would just stay on the whole time. And then I thought like, oh, maybe the SD card is bad. It was just like a whole bunch of things. But the fact that it's off is good. It means it's idle. And now I'm hoping that I can do ping nerves.local. And it's responding, so that's a good sign. And now, oh, there was something that I think I needed to do before that like allowed me to SSH to it. How do we do that? Did it talk about it in here and I skipped it? Hello Nerves, support page, target, quick. Once you have, you can build the bundle. Mix firmware, create a bootable disk, burn. This command will attempt to, yep, we did all this. There are many ways to connect Ethernet. When connecting to your device using USB to TTL, it was under here. So maybe this is what I did. But where did I see the info on actually how to do this? We didn't do the UART one. Terminal emulation program. HDMI, USB cable. Wireless. So this is what we must have done. If you want to use other network connection, but that's not it. So maybe this is what I need to read again. Nerves SSH. So we need to do Nerves pack, and I think we already have Nerves pack automatically in here in config. Does it go in here? Here's the Nerves pack that runs on the target computer. Use it with shoehorn. This is what we're using, MDNS. Oh, here it's looking for the ID pub keys. We do have them. No SSH keys found. Here we go. What is this saying? By default, the Nerves new project generator creates projects that includes your SSH public key from blah, 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 blah. It is possible configuration firmware key. So this should work because I have... Nothing is fucking easy. SSH. That's there. La 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 host. Nerves. Let's read the, what did it actually say? It is possible that someone is doing something nasty. Remote host identity has changed. Why would it say that? Oh, it's because of my local machine is confused. That's totally fine. I just need to remove it from my known host or something. Is this safe to show? I don't know. Here, let me just blur it for a second. So allow, I think I can remove that one. Okay, I did some surgery there. And now we will try to SSH again. All right, so guys, look at the error messages when you see something. I just assumed that there was a problem on the target side, but that made no sense. It's just basically, since I redeployed this on a firmware and reburnt it, I guess like the keys no longer match to the target fingerprint. And so like my local side was like, hey, that's not the right key. But now I deleted it from known hosts and now it's fine. So we can see we're inside of the Nerves VM, and we can do the normal like Elixir stuff, which is really cool. So this is just like getting it up and running. Now I'm going to go and try to deploy the Blinky example, which just makes the button, the little LED blink like you saw earlier. So let's try to make that happen. How the hell do you exit from this? God, this nerve stuff is not that easy for me. So what we're going to do now is go into the Blinky project. That was listed under here where it says example projects. So we're going to go and pull this down. We have that project now. We have Nerves examples. And we have Blinky. I think Blinky has a README. So we'll take a quick look at that. The hello world of the embedded world. Blinking an onboard LED. How exciting. it uses this thing called Deluxe, which is a hex package that controls LEDs. And it does like a lot of stuff around that. But basically, in the config directory, it actually has a bunch of these targets, right, already made. And when you set your mix target, it's going to pull in that specific file. Because you can see at the end of config.exs, it pulls in target.exs. And at the end of target.exs, it finds your environment variable for a mixed target and pulls in that file, right? So that's how that sort of chain works. And we're going to be pulling in the RPI 3A. So we don't need this number 1 anymore. So when you look at the RPI 3A, it has it's a Blinky config, and it has things called indicator, and this is a name of the LED for the Raspberry Pi. It's short for activity, I think. So that's about it. You can find out like what different things exist by connecting to, what's it called? Like, let me see if I can get in there. No, I can't get in there, right? I think in Linux it's is it dev class? Oh, I forget what the name of this is. Maybe it's sys class LEDs. And then you can see what LEDs are available for, you know, your system. And on the Linux one, it'll have its LEDs that are available. But I think most of these, you can see that they've defined it already. Some of these I think have more than one. So this one you can see has several. For the Beaglebone Black, the EV has 2, but pretty much all the Raspberries just have only one LED associated with it. This Grisp V2 has a few. So we're going to be able to access this through this name, I think. And I don't think we really need to do too much to actually make this work. It provides a configuration Blinky with indicators that's used by Deluxe. So Deluxe is going to look for this. That has a green LED. Here it tells us it's in sysclass LEDs directory. And then Deluxe itself is actually a gen server that gets started up, and we can look at that in a little bit. So how do we do this? We set our mix target just like before. We do a deps get, mix firmware, and burn, and voila, we're done. So let's go ahead and do that. So we should already have our mix target set, right? So then we do a mix, we go into Blinky's correct directory, then we do a mix deps.get. And that did that. And then we should do, it said mix firmware, I assume, right? Now it's going to build the firmware. This time I didn't bother with the SSH thing because we're not going to SSH to this system. And now we just need to do a mix burn. So I take the little card out again. I put it in my computer, wait for it to notice it. And do a mix burn. Burn, baby, burn! It pings me for my sudo password. It burns. We're all set. As soon as it's burned, it's ready to go. How are you guys doing? Now I put it back in here, but first I'm going to take the power out. Power in. Now we see that it read the OS. Please blink. Why isn't it blinking? Something's wrong. Oh! I got so scared. I was like, flashbacks of the PTSD. Okay, so you see that? It's blinking. We're good. Okay, so there's a lot of this like that I was learning where it's about like eventually what I want to do is attach a ultrasonic sensor and create like measure distance from the sensor with my hand. So it's like how far away my hand is and sort of make like a poor man's version of a theremin. So it creates a sound, and the sound is higher pitch when your hand's closer and lower pitch when it is further away. So this is the ultrasonic sensor. It's called an HC-SR04, I think. It has 4 pins associated with it. VCC, trig, which I think is trigger, echo, and GND, which is ground. VCC is like voltage something to something. I know like DD is like something to drain. But anyway, it's the positive voltage. But to like connect things to this thing, we basically have to work with these pins, and that's kind of hard to do. So instead, we're going to be using this thing. It's called a breakout board, and I'm not really sure if you can see here. Let me make it a little bit easier. You can see here, maybe that's best, that angle. So you can see like each thing is labeled, right? So this can match to the Raspberry Pi's whatever header pins, and then over here you have it called out what it is so that it's easier to work with. It's called a GPIO extension board. But we're not just going to do this. We could just do this. Why don't we just do this? Maybe I should just do this. No, I think we're going to attach it with this ribbon. And then this guy goes on a breadboard. And that lets us to like, so he'll go on like this. And then we'll be able to like easily connect things here, including putting the sensor here or something like that. And see if that works. So first thing first, we attach the ribbon to, how can I let you guys see this better? I had more room here. Oh, there's thunder outside. It was raining really hard here in France the other day. Like, I think it was yesterday. It was like sideways wind. But today it's not too bad. It's just like drizzling a bit. So I just take this. I don't think it matters which way it goes. I just attach it. I'm really bad at putting pins in. This one looks a little bent already. What the hell? Okay, so there we go. You see that? That looks like it's in. And now the other end here goes in here. Oops. It has like... That's not good. I'm going to switch these sides. You know, like, who makes these things? Why are they so hard? Is there like a trick? Do I have to... Oh, jeez. Okay. So I'm gonna redo this one. And hopefully this time it'll work better with the other. Here, I won't push it all the way in. Yeah. So now that works out. You see, like, this has this little, what is this called, indentation here. So it'll go in here and it won't block the rest of it. And this should be good. So now we have something that looks like this. And now this can go on the breadboard. We just like have it straddle the two sides. In case like I learned how this works yesterday. You guys probably know this, you know, but I didn't know. So I'll explain what this is. On this side, you have like all of these pins are connected horizontally, right? So it says like A, B, C, D, E, and then other side says F, G, H, I, J. And the first A through E on this side, you know, there's a split, right? They're all connected horizontally. So if there's any power going in on any of these, it like is as if they're all connected, and the same thing for the other side. And then you have these like minus and plus. These guys, I thought they were like, how do they they don't match horizontally, right? You see? These guys run up and down. So if you put a wire in here, like any of them, like that, then this whole thing, like let's say that this was actually carrying a current, then this whole thing gets that current, and then like you can like plug something in from here and connect it to the horizontal line, and you'll see how that works. The same thing goes for the minus. You just connect one minus. But the thing that's interesting is these two sides aren't connected, so you need to like join a wire from one to the other, I guess is very common. So you have like one of the minus go to the other side of the minus. We'll see all of that. But first thing first, we're gonna like get this we're gonna get this guy in. So we find the first pin up here and we just put it in the first pin row up here. and then push in. So you see that kind of matches. And now I just push in. And now you have something that looks like this. The very first one, which is called 3V3, that is the 3-volt power pin out, like positive, is on the first one. Yeah, and the first thing I was thinking of doing was sort of like, we know we're going to get a 3-volt output from this guy, right? So that's a positive charge. So why don't we connect that to the positive thing here? And I have an LED light. Here that I think we can make it turn on from the 3V3. There's also a 5V something, 5V0, I guess, 5 volt. But I don't know like about that. I know that like you have to be careful with voltage. So I think what I can do is basically take the 3-volt line. You see how the 3-volt line, now I'm like plugging into it. So that should be 3-volt. Red, I think, is typical for 3-volt. And then I can just connect it to the positive on any one of these, like here. And that'll run up and down this. So now this should, like, once this pi is connected, this guy here, he'll send a positive charge out here. And now this should like be getting 3-volt power this whole way down, right? Okay. So I think now I just want to like basically take this LED and connect it to somewhere in here. Let's just pick like 30, for example. There's two sides to this. You can see like a longer side and a shorter side here. It's a little less obvious when it's like like this. But the top one here is longer. I think the longer side goes to the positive. And then you want to put the negative side to the negative, which is what I just did, I hope. But obviously it's on the 30 line right now. It has no power yet. So we need to like put power on line number 30. So we just take, this is a long wire. Might have some shorter ones, 1 second. I have like all these wires. I didn't know how to like keep it together, so I took some hairpins. Alright, so I have a shorter one. And then I'm going to just plug it from this 30, this positive line here, to the 30. I think I have to put on this side, right? Because otherwise there will be nothing there, because these sides don't connect. And this will connect to ground. So we got to connect the ground here to the ground over here on the pi. So let's do that. Otherwise, there's no ground. Then the power can't flow. I think this is long enough. Let's try. So we just have to connect, yeah, it's definitely long enough. The ground on the pi, which is this one, ground. It says GND. There. The one that I just put over here says GND. And then we just connect it to any negative, anything on this negative vertical. All right, that'll let this LED, the negative side, connect to the ground. But there's a problem with this setup, is that this will like burn out something, because the LED is going to just try to like draw as much power as it can. So I don't really understand the physics too much, but like the LED itself will just like try to burn brighter, so it'll pull as much current as it can. So we need to basically add a resistor. This is a 1K resistor. It looks like this. Looks like a little guy. And we have to add that so that it basically like limits the amount of flow or current or something, right? This is basically saying you can't draw too much power. All right, so I basically made the resistor sort of like join the two sides of the 30. And now all I have to do is give it the power. I don't see, you can see that. So the resistor now, this guy, is joining the two sides of the 30. That's really hard to see. And so now I'm going to give power to this side by just connecting it to the positive. So now the power goes from up the power thing from the pi to the vertical power. That'll flow down to 30. It'll go into number 30. It'll go through the resistor, which is going to limit how much flows through, then go into the LED, then go into ground. God, I hope this works. I think it'll work. So what do we have to do now? I think all we have to do is this your first project with the breadboard? All of this is new to me. I've no idea how any of this worked before yesterday. I did a lot of Googling. I talked to my girlfriend and she's like, oh yeah, I had to do this in like, let's call it, it's a junior high or middle school. And I was like, what? I never learned any of this. So if I'm right, then as soon as I plug power into this, it should light up this LED without blowing it up. Let's try it. Ta-da! Do you guys see it? Oh, with the light you can't see it as well, but down here you can see it. And then when I turn it off, also it's blinking. So we did it. I should also... So that was the good news. We got the basics running. Now the next step, I like to learn things incrementally, right? So first, like, how do I burn? Like, even what the hell is any of this stuff, right? I didn't even know, like, when I got a Pi Zero, like, what am I connecting to? What does it do? So now I have a vague idea. It's running the Elixir Beam VM. We saw that we can SSH into it, which is cool. And that we can actually, like, do some programming. So let's look at, like, how that blink thing works. So if you look at the very top of this program, you can see that it gets all the environment variables for Blinky. And really, like, the most important ones are in the target, which is here. Like, we got ours from this RPI3A, which tells Blinky the indicators. And then there is the one other here, target, which is, it also gets passed in the RPI3A as a target. So Blinky gets this deluxe options is an array that's going to have a keyword list that has the indicators, and it has the target architecture. And so here we're sending a child spec that this is how you start up a supervisor in Elixir. And we're basically saying pass in those options so it knows the indicators and everything, and pass in something called initial, a keyword initial with the value blink on 2. And if you look at blink, blink takes in a color, that's C, a frequency, and then whatever options, right? And we're passing in a color and a frequency. I got so confused when I saw on, because I was like, this doesn't match this function description because it says the spec is an RGB color. Well, turns out that RGB color is actually on is an RGB color. It's just funny, you know. So anyway, we're calling blink with a color and a frequency. So that is just going to basically set up the initial blink instruction. So yeah, that's going to blink at whatever 2 hertz. One cycle per second. So does that mean it blinks twice a second? That's what 2 hertz must mean. Yeah, and then it starts up the children. So this automatically will start up this deluxe module with this initial setting, and so it's going to execute that. I don't think there's much else to Blinky. It's a very simple program. The config, mix target, pretty generic stuff that we saw there, and the application. I think that's really it. Okay. So this is basically, you're caught up to me. You know as much as me now, which is scary because look how slow I've been just doing this part. And the next step in my incremental kind of education for learning this is I want to be able to control that light myself. Not through like, because like, let's go back to showing this. Because right now, it's hard-coded. Hard-coded, there's no code. It's hardwired. I can literally say hardwired now. It's hardwired from the power into the LED. So even though we're controlling this guy to blink, right? This guy here, wherever he was. I think he was over here. I don't know. But I want to control this guy to blink now. But we can't do that since the power line is always on. And that's where we have all these other there's all these other pins here. One is called GPIO, general purpose input output. And I want to learn how we can basically, in that one, GPIO pins basically send out either an on or an off. I think with 3 volts also, so it's compatible with the same power voltage that's coming out of the current power. So basically what I'm thinking is take this wire and instead like plug it into one of these GPIO pins. So I moved it from power 3v3 to GPIO 17, it says. It's funny how they're not in order. It's like GPIO 17, then 27, then 22. Anyway, so now it's like the power is now, so this won't work, right? I think this won't work if I turn this on now because GPIO 17 probably is off by default. Why don't we try it, right? I can't imagine that this breaks anything. Like, I can't imagine this causes a short circuit. So let's see what happens if I just turn this on. Why don't you go down anymore? Okay. So I'll just plug this in and we'll see if this light comes on again. Nope, the light's not on. But the blinky part is blinking, you just can't see it. Maybe I can bring it in a little more. You can see it blinking, but this light is no longer on. But if I switch this from here to here, the light comes on. Surprising, right? It's like I can actually change this on the fly. I actually see another 3v3 right here. Oh, I guess there's more than one 3v3. So that works, but I want to switch it to GPIO 17. Here, we'll do that. Here. And I want to figure out how to control this guy through it. So that's what you're going to learn with me right now. And then after we learn that, we're going to learn how to use this ultrasonic sensor, how to read from it, and then how to turn that reading into a distance, and then how to make a sound, and then how to turn that distance into a sound, and basically make it smooth so that that sound is in real time. And then we have a theremin, right? So sounds pretty straightforward, but one step at a time. All right, so now we're going to go look at, I want to check what's going on here. So do you guys have any questions? I know I'm not like an expert here, but if you guys have any questions, I'm happy to answer. Just don't understand why Twitch isn't working. Maybe I'm on like the wrong, maybe I'm logged in wrong on Twitch. Oh, I have like 2 usernames on Twitch. That's why. How odd is that? Sorry, just 1 second. Aha. All right. Now I see what's going on. Oh, Findus, you're on Twitch. So I know Twitch is working. That's hilarious. So, why did I pick the Pi 2 model? So it's not Pi 2. Like if we look at nerves, does it say anything about what we can use? It's probably in system targets. So you can see here, like, these are the things that Nerves works on, right? And they're basically like microcontrollers that are pretty small. The thing with the 3, 4, and 5, these are like hefty, like, here, let me show you. This is my Raspberry Pi 5. Here, right? And this is the Pi 0. What? So you can kind of see, like, when you're looking at the size, the Pi 0 is much smaller. Oh shit. How did it just change? And so I wanted basically the smallest microcontroller to give me the feel of what real embedded programming is. Oh, you're on. Oh, Findus from YouTube. Stop confusing me. And yeah, like the Pi 5 has like full-on Ethernet, USB ports here. It has all of these ports, you know, USB-C, and you can run like a full-on Linux. So it felt a little bit like cheating to pick a bigger system. And for smaller systems than the Pi 0, they don't really like really exist. There's let's look at the Pi, Raspberry Pi, like offering. So I think these are smaller than the Pi Zero, the Pico, but they're so small that we can't actually like run nerves on it. They're like $5. This is, you can see that the Pi 20. Oh, I'm not showing my screen. Hold on. So here's the Pico. They're really small. They're like $5. And but they're going to be too small for nerves to run. And really like the Pi Zero, but this is version 2 of the Zero. And W, I think, means Wi-Fi, is 15. And you can see that it's different from mine because these pins here they haven't attached pins, so you have to do it yourself if you get that one. But I got mine with headers. So that's why. Otherwise I would have used the Pico, but it's too small. And all of these other ones, like the 3, 4, and 5, these are all like bigger models. I guess I could have gotten this one. I don't even know if they sell them. You see, like, well, maybe you can. How much are they? Wait, why does this have so much memory? 500. What? I guess it has as much. Anyway, that's why I picked the Pi Zero. Alright, so what we need to do is figure out how to control the GPIO, and I don't know how to do that yet. So we're gonna look it up. We're gonna say like GPIO nerves. I think these are the same. Yeah. Circuits GPIO. I think it's the same thing. We want to look at the latest version. Okay. Why is my system theme light? Oh, because this is a new laptop. I probably never set it to dark. It's like, why does it hurt my eyes? Alright, so getting started on Nerves and Linux. So we need to add, so let us, maybe, what do we do? Should we take Blinky and turn it into what we want? Or should we start raw? I think we should start raw. We'll just go back to our other application that we already just built. And it was called Hello Nerves. We'll rename Hello Nerves to like GPIO test. And then inside of our config, I guess we need to add into target dot here. Where do we add the dependencies? Where do the depths come in? I'm confused. Oh, I just forgot Elixir, that's why. I don't know why this is unhappy, but we got a lot of depths in here. We don't have circuits, right? Circuits, no. Dependencies for specific targets. I'm not sure what that's about, but here we will add circuits underscore GPIO, comma, we want something that's greater than or equal to 2.1. And this is doesn't really say, like, what do I say? Control GPIO. Okay, so now we have that. I should be able to do mixsteps.get. It already has our target. Syntax error, syntax error. I forgot the comma. Okay, so we have that in, we have this dependency now. Da 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 da. Okay, so now let's try to understand what we have here. A general purpose input output IO. Is this hard to read? Is this too small? Let's do this. Is just a wire that you can use as an input or an output. It can only be one of two values, 0 or 1. A 1 corresponds to a logic high voltage like 3.3 volts, and a 0 corresponds to 0 volts. The actual voltage depends on the hardware. Here's an example of turning an LED on or off. This is a resistor. I don't know what this is, and this is ground. To turn on the LED that is connected to the net or wire labeled GPIO 18, you need to open it first. The first parameter to open is called the GPIO spec and identifies the GPIO. The Raspberry Pis are nice and provide string names for GPIOs. Other boards are not as nice, so you always have to check the string name for this GPIO is GPIO 18. Unless you're on a Raspberry Pi 5. So we type in something like this, and then we get back OK plus the actual GPIO reference. Then looks like we can write to it, and we can close it. The call to close is not necessary since the garbage collector will free up unreferenced GPIOs. It's a good practice though, since backends can enforce exclusivity and prevent future opens from working until the GC occurs. Input works similarly. Here's an example of a button with a pull-down resistor connected. Let's try to find out, like, what is this picture here? What is this called? Like, common circuit symbols. What am I looking for? This, like, it's like a triangle with a line. This thing. Oh, it's an LED. Turning an LED on or off. Right. That makes sense now. This is the LED. A resistor to make sure the LED doesn't pull too much. And the GPIO is the input. Yeah, that's exactly what we're doing. We're going to do exactly this. Okay. That's literally what I have wired up right now. Alright, so let's look at this one. Well, this is input, right? Let's not read input just yet. Let's just try to get this going. I don't think I need any of this then. I think I can just program this. Let me make sure I can first build the firmware and still SSH into this. So let's do that. We just added the GPIO as a dependency. So I think what this means is that when we SSH in, we can make calls to it. Let's test out this theory. So we just did debsget, so we should be able to then do firmware. Then we should be able to do a firmware burn. There has to be a better way of like, or upload it to a device with mix upload. Like what? Wait, what the fuck? Let's learn about that after this. I'll just do this once more the old-fashioned way. We'll burn it now. Was it firmware burn? Mix burn. It's burning. It's burnt. We take it out. Need tweezers to take it out of this guy. Is there like an eject button? It's so hard. Okay, so now I put it back into the Raspberry Pi, and we'll plug it in to power. Alright, this one is not running Blinky, so it shouldn't blink. We'll just see if we can SSH into it. All right, I'm thinking that's enough time. Ping nerves.local. There it is. Looks like it's connected. like every time I burn it screws up the SSH known host, so I just have to edit it. Alright, so we're in. And now I think we should just be able to type this in. Circuits.gpo.open GPIO. Which number did I connect it to? Looks like 17. And we want output in this case, and we want to capture this in, let's just get result. So result is okay, so it worked. So we can do like okay comma GPIO is equal to result. Now GPIO is just this part. Now we should be able to write to it. I can't tell what's going on. Is this... Vendis, are you still there? Is this thing working? Oh, maybe I can see here. Oh, I'm not getting the latest like chat updates for some reason. Why is this? Doesn't matter. So now I've gotten the GPIO, I should be able to write to it. Let's see if this works. I'll point the camera down to the thing here. All right. We see this. This is the light that's off. This is connecting GPIO 17 to the positive right now. And then this positive goes to line number 30 with a 1K resistor, then the LED that goes to ground. And this ground is connected to the ground on the Raspberry Pi Zero. So now when I type in circuits.gpio.write GPIO, comma 1, this should turn it on. Hey guys, do you see it? Does it look on to you? It's on to me. It's very faint. Let me see. You do see it. Okay, cool. And now when I type in GPIO close, no, I want to write 0. It turns off. Isn't that lovely? So we figured out how to control a light. Should we like add maybe 3 lights and make them just blink in a random pattern? Or should we go straight into the ultrasonic thing? Kind of just trying to decide. The problem is like if we make it blink, spend time doing the blinking, then I have to get ready for this conference and I want something to show for it. So would it actually help me? It would be cool, but I think we can skip it. But it's cool, like, I think this tells us like how to do it, right? And then we can call close. And that closes it. Now if I try to read from it or write to it, it'll probably give me an error. Yep. All right, so now we have to figure out how to handle the ultrasonic thing. Where did I put it? All right, this is an HCSR04. Let's look it up. Yeah, we have the equipment. Here's the ultrasonic sensor. And I have something to make sound. I basically have a USB, audio output plug, so the Raspberry Pi can make like a silly sound. But now I feel really out of my depth. This looks just like mine, right? VCC, trig, echo, ground. This must be like one's input, one's output, I think. And this is power. VCC is power in, the positive, and ground is negative. So the only issue, this takes in 5 volt, which is okay because the Raspberry Pi has a 5 volt. Oh wait. No, yeah, so we connect a 5 volt into from the Raspberry Pi to VCC, and then the ground from this guy to the ground and the Raspberry Pi. So let's just do that now. So we'll just take the ultrasonic sensor, and I think I'll make him point outwards so that like we can test distance this way. We'll move him over here. I guess. Maybe one more in. All right. So we'll keep it over here. And then we have these 4 pins here. We'll connect ground to ground. So we need a black wire for that. So the ground is the first on the left here. I'll just connect that to ground here. So now you can see ground is connected. And And then power is VCC, so I need a red cable for that. It needs to go a little further, so let me get a longer one. So 5 volt is here. Is there another one? Looks like only one. It says FV5V0. There's 2 of them here, so I'll just pick this one. Oh, why don't I just like not connect it all the way here? I'll just make this one is, this positive line can be the 3 volt positive line. This positive can be the 5 volt one. So I'll just take a small red and I'll connect the 5 volt to the positive here. So now this positive vertical line is all 5 volt. And now we can just take something from this 5 volt one, like, you know, just here, and connect it to the power for the ultrasonic sensor. So theoretically now it should be powered like as soon as the Pi is powered up. But we need to figure out how to use the echo and trig line. So we gotta read about that. Let's see how this works. I don't know. Looks like Arduinos are a little bit different. God, doesn't this look simpler? No wonder. Oh, it's not telling us like in high level how this works. So this is what the website looks like, and they say to, I don't know what they're doing here. Oh, here's their ground and VCC, and you can see it attaches to the ground and positive here. That goes to the ground and positive for the Arduino. And then they have these 2 echo and trig pins going in. Trig and echo are connected to, so trig is 9, echo is 10. 2 flows, duration and distance, which will hold the length of the sound wave and how far away the object is. Duration and distance. We declare the trig pin as an output. Okay, so we need to make an output. Let us exit out of here. Oh, I like killed that. Okay. So we need to make a program now that will guys, I'm so tired. We gotta make an output pin. So where do we do this? Alright, so we're going to need some functions in here. And what were they? GPIO. We don't need this. So we're going to need to define something as an output. No, we'll just use the whole name just to make it clear. And we'll need a pin for the output pin. We'll just fix those later. So this should create the output pin. What did it call it? Is the trig pin the output pin? Yeah, trig. Why don't we call this right? And the echo is the other guy. And then we also have to figure out how to do input here. It looks like it's the same thing. Alright, so now we have a trig and we have the echo. And then we can do reads and stuff later. Let's see what happens here. So we kind of have the equivalent of this. I don't know what this serial means. Oh, you're like, keep updating the camera. Now in the loop, what we want to do is first set the trig pin low for 2 microseconds to just make sure that the pin in low first. Where does it tell us like what trig does? Anyway, then we set it to high for 10 microseconds, which sends out an 8-cycle sonic burst from the transmitter, which then bounces of an object and hits the receiver, which is connected to the echo pin. Echo is the output, right? No, right. It's writing to us, so it's the input. When the sound wave hits the receiver, it turns the echo pin high for however long the waves were traveling for. Oh, that's why it's called echo, because it tells us how long the waves were traveling for. So the longer the echo is on for, the further it is. Let's see, I wonder how GPIO can handle this. Oh, here's something called interrupts. If you'd like to get a message when a button is pressed or released, call the set interrupts function. You can... Well, it's not always a button though, but I think this is what we want. Note that after calling set interrupts, the calling process will receive an initial message with the state of the pin. This prevents the race condition. Alright, I don't think this is what I want. Convenience functions. Having to open then read and write can be cumbersome. Circuits to have a new pair of functions. Write 1, read 1. Not sure how this works. Oh, just write 1. Read 1. Don't get it. Oh, it's just basically reading it once. Yeah, we don't need that. I think we're going to need to use set interrupts. Trigger is not a function. Oh, it is a function. Oh, these are types. What am I doing? Where was I looking at the trigger stuff? Oh, it's called interrupt options. I think it's set interrupts then. Here. That's where we get triggers. No, we pass in the triggers that we want to listen for. Sent based on the trigger. None, no notification. Send a notification when the pin changes from 0 to 1. Send a notification when the pin changes from 1 to 0. Both. So I guess we want both. So why don't we write a first pass of this code where it listens for both. And then we just send like we just call the, whatchamacallit, what was this one called? The trigger pin. We declare trigger pin as output. Now in the loop, we first the trigger pin for low for 2 seconds. So we just kind of make it 2 microseconds. So we just make sure it's low. Then we set it high for 10 microseconds. I wonder, so delay microseconds. So we say high and then we wait. This is kind of useful. Like we got to figure out how to get something to write. Like it would be nice to say digital write pin high 10 microseconds, right? That function we need. Alright, but let's first figure out like other ways. Is there anything better than this? That talks about how this works. Is there a user manual? Trigger low 2 microseconds. Trigger high 10 microseconds. That's what the other guy was doing. Then back to low. So this is probably the same data sheet. Okay, let's read this. 2 centimeters to 400 centimeters. How far is 400 centimeters? The data structure you receive? For what? For the interrupt? Sorry. Oh yeah, the type. That's what we're talking about. Yeah. So in set interrupts, we get back OK error. We pass in the triggers. So these are going to get called as messages to the process. Notification messages will look like this. Circuit GPIO, spec, timestamp, value. We have to be careful about this. Okay. Using I/O trigger for at least 10 microseconds high-level signal. So that's where they had the 10 microsecond thing. The module automatically sends 840 kilohertz and detect whether there is a pulse signal back. All right, so this is like what it emits out of the thing. It doesn't tell us anything. If the signal back through high level, time of the high output I/O duration is the time from sending ultrasonic to returning. Test distance is high level time, how long it's when the high velocity of sounds, 340 meters per second divided by 2. Well, that makes sense. So we have 2 questions here. How to send trigger input signal needs to be 10 microseconds. How to measure return signal. Alright, those are kind of like 2 things we have to figure out. I'm going to take a quick break and get something to drink, and then we'll continue with this. If you have any ideas, let me know, but I'm thinking that we need a function that sends it for at least 10 microseconds. We could try using Elixir to see if it can handle microsecond timing. I'm not really sure how good it is, but at the same time it says like it needs to be 10 microseconds, but not necessarily longer. Doesn't really say. All right, we're going to figure this out. Be right back. I'm making some tea. How are you guys? Anyone still here? I think we can use, maybe there's like a, what is pulse width module? Oh my. %, duty cycle. Oh, so I can send the pulse that's on and off? Huh. Seems like software PWM should not be used in high frequency. If you're trying to drive a servo or dim an LED, look into PWM. Many platforms have PWM hardware and you won't tax your CPU at all. If you need to implement a wire level protocol to talk to a device, look for a Linux kernel driver. Oh my god. PWM hardware. Hardware PWM kernel module isn't being built in the nerve system. What is, since Pi had so most people had either used I2C PWM module or used a PIG PIO DM8. Oh, so what is this? Is this it? No. Didn't they say you can use this on nerves? In the nerve system. This must mean it's in the Linux. Software PWM, what does this mean? Which is a wrapper, okay. What the fuck was that? What were we looking at before? Not that one, but modules. Have you already connected to the sensor? Not yet. Still figuring out, like, it looks like it's kind of complicated to read. We have to send a 10 microsecond burst or pulse to the thing. I'm not really sure how to send a 10 microsecond one. That's why I think I need to use something like this. Duty cycle. I don't really want a duty cycle. I just want to set something for a certain amount of time. I mean, this kind of works. But maybe this is what I need. Hardware PWM. I see. So this guy wrote something that schedules something to send a pulse once a second here, for example. And here's the function that turns it on. Here's the function that turns it off, and it spends half its 50%, which was that graph we saw earlier. 50% means it's half time on, half time off in this 1 hertz cycle. But we need something much, much faster. So this version won't work. Do you have a deadline to this? Yes, I have a super... My deadline is... I'm doing a talk on this at a conference. I fly on the 7th, I think. So, on Sunday. So I need to have this built by, by then. And for me, I think that's plenty of time. I also have to work, I forgot. I wonder if I have any meetings. Nope. So can't do this full time. This PWM scheduler is going to be a lot more annoying than I thought. I thought like there would be a function that basically says send for 10 microseconds, but there is none. What is this saying here? We need faster, more. If we know, we should consider using. Let's just Tokafish. Yeah. So this is what we looked at here. Hardware PWM feels smoother in changing. I see. So this would be 800 hertz, I'm guessing. Hardware PWM. Where is that function? Oh, here it is. Sets up a specific pin as a software PWM and sets the current duty cycle. Okay, hardware sets the current and frequency. So frequency, I'll have to assume this is hertz. So I think we can use this. Let's do this. Let's try this out. Alright, so to use this module, how the hell do we use it? Doesn't it usually tell you like doesn't it tell you like how to put it, like the name of it? I guess it had. Kind of weird that no one else is like. Hardware PWM, what does that mean? $12, $13, $18, $19. We might have to use ChatGPT. Let's see. Because it's getting like really annoying. Okay, let's see. What is hardware PWM for Elixir Nerves? PWM is a way of simulating between high and low at certain frequency and duty cycle. Software PWM, you can implement PWM in user space by toggling GPIOs from Elixir code. This is easy but inaccurate, right? Hardware PWM, like many socks, have dedicated hardware timers. When you use them, the kernel configures the peripheral and the PWM is managed precisely. I see. know what any of this is. Circuits PWM. We did not see that. Alright, so it sounds like so this, let's see what this is. Yeah, that's what I thought. Circuits PWM. So it's probably just hallucinating this. Yeah, oh. Alright, this is what we found. So PIGPIOX will use the hardware PWM on a Raspberry Pi. Okay. Oh, my partner is here. I probably have to go. This will be the main thing to figure out how PWM works so that we can send the 10 microsecond pulse, and then we'll learn how to read it. I will end now. Thanks so much for hanging out with me, and I will talk to you later. I think I'll also be streaming more of like my actual work, which is using TypeScript. And it's open source project, so there's no problem doing that, so I'll be doing that more.